News from China say the Chinese have broken their own and the global speed record for magnetically levitating trains, which you might know under the name Hyperloop. Let's have a look. I find news coming out of China generally somewhat difficult to interpret. In this case, all we have to go by is an article that appeared in the South China Morning Post. They report that the China Aerospace Science and Industry Corporation, CASIC for short, has made a significant breakthrough with its latest test. There are no further documents to support this supposed breakthrough. But while I don't have much trust in the Chinese government, I have a huge lot of respect for Chinese scientists and engineers, which is what makes me think it'll probably be mostly correct. What it means, though, is a different question. The new transport system from CASIC is a magnetically levitating train that travels in a vacuum tube. These trains are also known as maglev, short for magnetic levitation, and yes, that's basically what Musk means by Hyperloop. Such transport systems dramatically reduce friction both with the ground or rails and, most importantly, with air. The test facility is located in the northern part of China and is, for all we know, the biggest of its kind with a test tube of about 2 kilometers length. Construction on the test facility officially began in April 2022. Last year in the summer, they reported having reached 452 kilometers per hour, which made the Chinese maglev the fastest train in the world. In October, they said they'd reached 623 kilometers per hour under non-vacuum conditions. They now report that they've exceeded this speed, presumably with some amount of vacuum, but they don't say exactly what speed they've reached. Their goal is to reach 1,000 kilometers per hour. Just for comparison, a typical passenger plane flies something like 800 kilometers per hour. The China Post also says that the test allowed them to check that various components of their technology are working as desired, most importantly, the magnets. This is all very good news. The biggest challenges for those systems are maintaining the vacuum in long tubes over potentially hundreds of kilometers and avoiding accelerations. Getting such systems up to speed is no small feat. It isn't easy to maintain a good vacuum in a tube that long that needs very precisely shaped parts. And at that high speed, even the smallest bump or wiggle could be a disaster. If you have tubes over long distances and you put them on the surface, you'll have to cope with the expansion and contraction due to temperature changes. If you put them underground, you'll have to cope with geological tensions. Both of these are small effects, but at 1,000 kilometers an hour, even the smallest deformation can be an issue. And the issue is that inside the thing, it might get very rough. You can actually see this in this footage from a Virgin Hyperloop test in 2020. Pay attention to the vibration. It's noticeable, but you may say it's not too bad. Then again, they reached a velocity of merely 100 miles per hour. So I think it would be very interesting to get some data on what's going on in that Chinese maglev. Does it make sense to build such a transport system? Well, that depends on how expensive it is. But generally, I tend to think if you have a country as large as China, it does make sense. Even if you don't use it to transport people, there's a lot of stuff you might want to transport that doesn't care very much about vibrations. Steel, concrete, clothes, chopsticks. But about those vibrations, the company Virgin Hyperloop, of which we saw the test footage, decided 2 years after the test to focus on transporting freight. However, in December last year, they announced they'd be shutting down, quoting financial problems. So I'm somewhat skeptical about the passenger friendliness of those machines. But I still think the Chinese might be getting something out of it. If nothing else, it brings them good press. I've been very critical of the so-called hydrogen economy, but I've recently reconsidered my position because of an interesting development. A few months ago, scientists drilled a hole in southern France to measure methane levels. But instead, they found hydrogen. Indeed, the French might be sitting on top of one of the biggest naturally occurring hydrogen reservoirs in the world. And it might not be the only one. There are now startups all over the world searching for this stuff. Let's have a look. This video comes with a quiz that lets you check how much you remember. Hydrogen burns cleanly with oxygen to water while creating energy. That makes it sound like the ideal fuel. But there are a few problems. At atmospheric pressure and room temperature, hydrogen is a gas, and to handle it, you need to either cool it or, more commonly, put it under pressure. Hydrogen is also generally nasty to deal with. It's such a small atom that it creeps into any other material and degrades it rapidly, a problem known as hydrogen embrittlement. But hydrogen is used in the chemical industry for all kinds of purposes, exactly because it reacts so readily. At the moment, it's predominantly produced from methane, also known as natural gas. The reason isn't hard to see if you have a look at the chemical formula for methane. That's CH4, which is a lot of H's there. You will also have noticed that methane has that C in there. So what happens with that? Well, to get hydrogen out of the methane, one uses a process known as steam reforming, in which one combines the methane with water, which produces hydrogen plus, wait for it, carbon dioxide. Yes, so if we produce hydrogen from methane, that leaves behind carbon dioxide. Now, the fans of hydrogen say that you can produce the hydrogen from water with renewable energy and also use it for energy storage. And yes, that's a nice idea in principle, but in practice, there are only a few tiny test facilities for that, and using hydrogen to store energy is extremely inefficient. You can make hydrogen from biogas, that's methane produced basically by letting agricultural waste rot away. Biogas production exists and it does work, but it has the rather obvious limitation that you need land to grow all the bio stuff that you let rot away. And if you crunch the numbers, biogas will realistically not supply enough hydrogen to power or transport vehicles. And that's why I think the so-called hydrogen economy is somewhat of a joke, because it'll end up basically being natural gas. But geologists have known for quite some time that there are hydrogen reservoirs in Earth's crust. This in and of itself is somewhat surprising because, as I said, hydrogen is a very small molecule. You expect it to escape. Even if it doesn't escape, it likes to react with something that contains carbon, and then you get the carbon problem back. It turns out, though, that hydrogen doesn't really care what geologists think it should be doing. There have been a few reports going back to over a century of hydrogen bubbling out of the ground, sometimes leading to accidental explosions. A particularly remarkable case is a borehole in Mali that was shut down in 1987 because the gas coming out of it tended to explode. It wasn't until 2012 that someone figured out it was almost pure hydrogen gas and made a business out of this. But more often, hydrogen is a small fraction of gases that escape from the ground. Estimates say that the new hydrogen deposit, which they found in southern France, contains between 46 million and 260 million metric tons of hydrogen. This is roughly comparable to how much the world produces in 1 year, which is 96 million metric tons. That'd mean it's basically 1 year without the greenhouse gas emissions coming from the usual hydrogen production. Not bad, but not a game changer in and of itself. The game changer is that there could be more, much more, and it might be renewable. Just how these hydrogen deposits come into being is somewhat unclear, so no one really knows how many there are. But the leading theory is that the hydrogen is produced when hot water underground reacts with hot iron-rich minerals like phosphorite and other olivine stones. The oxygen in water bonds to iron, freeing up clean hydrogen atoms, which rise and get stuck in porous rocks, much like methane. Depending on what the geological layers are above the production site, the hydrogen doesn't necessarily escape to the Earth's surface. But if you drill into the rocks, the hydrogen escapes, et voila. If that theory was correct, this would be very exciting because it'd mean that these hydrogen reservoirs can replenish if more water runs over the hot rocks. They're basically geothermal wells in which the hot rocks produce hydrogen. The US Geological Survey has estimated in a 2022 report that there could be tens of billions of tons of naturally occurring hydrogen cached globally. If only 1% of this could be extracted, that could cover 10% of the world's energy needs. This is why in the past years, hydrogen mining startups have sprung up everywhere, such as the Denver-based companies Coloma and Natural Hydrogen Energy, the Spanish company Helios Aragon, the British company H2AU, and the French Française de l'Énergie. And all that sounds very good, and I'll admit it does make the entire hydrogen economy thing sound much more plausible, yet I'm still kinda skeptical. As we've seen in our earlier episode on geothermal energy, if you dig into the ground, all kinds of gases can come out, including methane, carbon dioxide, and nasty sulfuric stuff. This makes me think it'll be very rare they get almost pure hydrogen gas. More likely they'll have to separate it from the carbon-containing stuff and then figure out what to do with the rest. Whether this makes sense economically, energetically, and environmentally, only time will tell. Sometimes people ask me why I'm now doing science news. It's so that you can fully appreciate the drama of scientific discovery, in which one result contradicts the previous one and the next one finds a flaw in this other one. I think the entertainment value of science is greatly underappreciated. And quantum computing is without doubt one of the most dramatic areas at the moment. On the one hand, you have people claiming it's the next industrial revolution and it's going to change the world. And on the other hand, you have people saying it's all hype, quantum computers are interesting but useless. This new paper supports the latter camp. Let's have a look. Quantum computers are devices that exploit quantum links known as entanglement. And no, that's not what Einstein meant by spooky action at a distance. Entanglement doesn't exist in conventional computers, and because quantum computers have these additional ways to encode and handle information, they can perform some calculations much faster. The relevant part of the previous sentence is that they can perform some calculations much faster. It isn't the case for all calculations. Nevertheless, the calculations that quantum computers can speed up cover several commercially relevant cases, such as quantum chemistry, that plays a role in material design and drug development, as well as logistics and finance. This is why there's so much hype around quantum computers and that talk about a new revolution. On the other hand, there are a lot of practical problems in making quantum computers work. I mean, besides the problem that no one understands quantum mechanics, though there's that. The real issue is that these quantum links are incredibly fragile. Depending on how you create them, they might last microseconds to a few seconds, but that's about it. And your calculation needs to be done within that time. And I mean, I do calculations for my financial management within a few microseconds, but it's probably not a good thing. There are many approaches to quantum computing that differ by how you physically realize the quantum bits, qubits for short. I've talked about this in several previous episodes, but all these approaches have this problem in common. The quantum information is very sensitive to disturbances, which brings in errors. These errors can be avoided by introducing redundancies, but that requires making the computers larger, which brings in more problems. What this means is that the need for error correction moves useful quantum computers further into the future, and no one knows how far. That's unappealing for investors. And this is why in the past years, some physicists, like for example John Preskill, have pushed the idea that even noisy quantum computers can be good for something. If that was true, it would do a lot against the criticism that quantum computing applications are far away and might remain far away forever. Last summer, IBM said they'd done it. They'd done something useful with a noisy quantum computer, and the New York Times celebrated this success. The new paper now puts the IBM achievement into doubt. So, you see the drama. In last year's paper, the IBM team explains how they used a noisy quantum processor with 127 qubits called the Eagle processor to calculate what's called the trotterized time evolution of a 2D transverse field Ising model. The Ising model is a model of coupled quantum spins, and the trotterized transverse field and so on means it's a special version. This model is interesting if you find that kind of model interesting. To my best knowledge, it doesn't have any uses. However, the type of calculation is difficult to do on a conventional computer, which is what makes it an interesting test. The IBM group claimed that their quantum chip outperformed any calculation that could be done on a conventional computer, and that, quote, "there is indeed merit to pursuing research towards deriving a practical computational advantage from noise-limited quantum circuits." The authors of the new paper now say that IBM was somewhat over-optimistic. They found a way to do the calculation on a conventional computer, and they managed to do it faster and better than IBM could on their noisy computer. Basically, they show that conventional computers outperform the quantum computer also on this task. They write, "We can perform a classical simulation that's significantly more accurate and precise than the results obtained from the quantum processor." You can see this very nicely in this figure where the dots with the error bars are from the quantum computer and the smooth line going through them is from the new calculation. So, another supposed quantum achievement gone. That's happened a few times before, that one group claimed they'd done something spectacular on a quantum computer, just that later another group did it on a conventional computer. The most prominent example was probably Google's 2019 claim that they had proved a quantum advantage. Back then, the scientists from Google published a paper in Nature claiming they'd done a calculation on a 53-qubit quantum computer, which would have taken 10,000 years on a conventional computer. The 10,000 years claim was swiftly questioned by IBM, and indeed it was later done by a Chinese group on a conventional computer in only 5 minutes. Then again, maybe that just means that 10,000 years in Silicon Valley are worth 5 minutes in China. This new result matters because it's once again showing that conventional computers are so advanced already that they're a very strong competition for quantum computers, and that'll probably remain so for quite some time to come. This is really bad news for anyone who has invested into quantum computing. I got quite a few questions about a paper that supposedly revolutionizes our understanding of the universe by throwing out energy conservation. The questions came in two varieties. Can you do that? Isn't energy always conserved? And isn't energy conservation violated anyway? I thought it'd be interesting to clear this up because I think the idea isn't remotely as crazy as it sounds. Let's have a look. Astrophysicists have invented two types of mysterious stuff, dark energy and dark matter. It's not just because they like the word dark, though maybe that's that. It's because they need the dark stuff to make the predictions of their theory fit with observations. But just what dark energy and dark matter is made of, or where it comes from, has remained a mystery. They need dark energy to make the expansion of the universe speed up, and they need dark matter to make galaxies rotate faster, because that's what observations require. The idea that this happens because energy just isn't conserved and comes out of nowhere is quite appealing. If you have extra energy, it sounds plausible enough that you can make the universe blow up or speed up galaxies. And if you can do that, maybe we can also power cars with nothing. But the problem is to make this compatible with Einstein's theory of general relativity. Albert is really worried about that part. Before we can talk about general relativity, we need to sort out what physicists mean by energy to begin with. It's not what we mean by energy in everyday life. Usually we talk about energy as something we need to do things. Your phone needs energy to work, your car needs energy to run, you need energy to follow what Sabine is saying, and so on. Well, in physics, this is more specifically called free energy, not the useful part of energy, so to speak, the energy that we can do something with. However, like most Twitter comments, most energy is not of the useful type. Take, for example, the air molecules around you. They have kinetic energy because they're moving, but you can't do anything with that. Your phone won't just magically charge if you hold it into the air. When physicists talk about energy conservation, they mean all that energy, the useful and the useless one. This total energy is conserved in everyday life to good approximation, which means actually, strictly speaking, it's not conserved. Yes, sorry, energy really isn't conserved. Energy can increase or decrease whenever space itself changes in time. The easiest way to see this is to imagine a part of space in which you have quanta of light. Those are the photons. Photons have a wavelength that tells you the color of light, and the wavelength also tells you the energy. The longer the wavelength, the lower the energy. The total energy in those photons is their number times their energy. Now imagine that space expands. You still have the same number of photons, but now their wavelength is longer, so their energy is lower. So the total energy has gone down. Where did it go? It didn't go anywhere, it just isn't conserved. This isn't merely theory, it matches observations. The lack of energy conservation in the expanding universe is why the cosmic microwave background is so cold today. It's a really tiny effect though, and doesn't help us with the energy transition, I'm afraid. So energy really isn't conserved if space can stretch and shrink, which is what happens in Einstein's theory of general relativity. However, in his theory, we have a more complicated type of energy conservation. In essence, it says that if energy isn't conserved, that's because space changes in time. The change in energy needs to match the change in space. It's called the covariant conservation law of the stress-energy tensor, in case you want to impress your neighbor. But for the rest of the video, I'll just call it generalized energy conservation. And this then brings us back to the opening question. Can we fiddle with this generalized energy conservation to explain dark matter and dark energy? The brief answer is no. But that's for an interesting reason. It's because so long as you describe gravity as the curvature of space, as you do it in Einstein's theory, this conservation law is always fulfilled. It's a mathematical identity. You can't get rid of it. What this means in practice is that any attempt to throw out generalized energy conservation has the consequence that a new contribution appears in the equations that makes up for the mismatch. And that new contribution, guess what? That can look like dark energy, and that can look like dark matter. But it's nothing new. It's mathematically the same thing. You just interpret it differently. And that's what this new paper is about. Now, this is a single-authored paper in a so-so journal, so one doesn't expect much. But it's actually a fairly reasonable paper for the state of art in the area. I'm really trying to be nice, okay? Don't make it harder than it is. The author uses this energy non-conservation approach to arrive at specific predictions. He says that this leaves some small features in the cosmic microwave background, which is what people usually predict in this area. The issue is that even if that prediction would turn out to be correct, there are like 100 or so other models giving the same prediction. But personally, I think that one shouldn't dismiss this idea too quickly. Because you see, the problem with dark matter and dark energy is that we know too little about it. If it came about in a particular particular way, for example, by violating this generalized energy conservation, then that makes it more specific, so it reduces the ambiguity. This isn't to say that I think it's correct, but to me it makes more sense than just cooking up a few hundred of particle physics models. Though I'm afraid we still won't be able to charge our phones from dark energy. As everyone knows, there are 3 different types of magnetism. So I was a bit surprised to learn of a new 3rd type of magnetism. Didn't we already have 3? What's new? I had a look. The magnets that we all know and like are what physicists call ferromagnets. Materials with these properties include most famously iron, which the name ferromagnet derives from, as well as nickel, cobalt, and many alloys. When it comes to the alloys, it's apparent already just why magnetism is so confusing. Take steel as an example. Depending on the crystal structure and fabrication, some types of steel are magnetic, others not, and some are magnetic in some places. None of them will stick to your forehead after vaccination. Contrary to popular belief, magnets also don't stop working if you put them into water.
All I know about magnets is this. Give me a glass of water, let me drop it on the magnets. That's the end of the magnets.
Though I'm sure what Trump had in mind there was electromagnets, which I indeed recommend you don't throw into water, or if you do, at least don't sit in the water at the same time. Where does magnetism come from? Magic. Well, the electromagnetic interaction is one of the fundamental forces of nature. It doesn't come from anything, at least not that we know. It's rather that other things come from it. For example, fridge magnets, or as Richard Feynman put it.
So I'm not going to be able to give you an answer to why magnets attract each other, except to tell you that they do.
But we can understand to some extent how magnetism in materials comes about from this fundamental magnetic force. It's that atoms all have electrons hovering around them, and that makes each atom a tiny little magnet where the strength depends on the type of atom. The question is then how these individual magnets combine in materials. In ferromagnets, what happens is that the magnetic moments of neighboring atoms like to align, and they hold on to this alignment. This is why you can magnetize these materials. In most materials, that doesn't work because the orientation of the tiny atomic magnets won't stay aligned with the neighbors. But even ferromagnetic materials will lose their magnetization if you heat them up too much. That's because then the atoms shake around too much, basically. So maybe Trump was speaking of boiling water. I'm sure that's what he must have meant. In any case, that's ferromagnetism, which most of you will be familiar with. The second kind of magnetism is called diamagnetism. Diamagnetic substances react to magnetic fields by weakly repelling them. An interesting example of a diamagnetic substance is water. You can see this in this little demonstration in which the magnet seems to attract the air bubble, though actually it repels the water. Diamagnetism had its moment in the sun when a group of scientists demonstrated it by making a frog levitate. Since humans, like frogs, are basically big bags of water, I suppose you could levitate humans the same way if only the magnetic field was strong enough. You know, I think if CERN said they want to build a magnet strong enough to levitate humans, I'm pretty sure they'd have an easier time getting money. So we have ferromagnetism and diamagnetism, and then there's paramagnetism. Paramagnetism is similar to diamagnetism in that it's a response to a magnetic field, but paramagnets are attracted to rather than repelled by the magnetic field. Some paramagnetic materials are oxygen, aluminium, and platinum. That makes ferromagnetism, diamagnetism, and paramagnetism. By my count, that's 3. And then I read this press release which says that a group of experimentalists in Switzerland has experimentally proved a third branch of magnetism termed altermagnetism. All right, but we already have 3, right? I read the paper and they count ferromagnetism, anti-ferromagnetism, and altermagnetism. Oh dear. But don't despair, we can sort it out. Remember that in a ferromagnet, the atomic magnets react strongly to each other and they like to align. In an antiferromagnetic material, they also react strongly to each other, but they don't want to align. So you get a mix of one and the opposite direction. This happens, for example, in chromium. An antiferromagnetic material then has no total magnetization and won't hold stuff to your fridge, but they're good at holding orientations of the tiny magnets, which is why they're used in computing, for storage and for other things. The magnetism now is a new type of magnetism in which the directions of the atomic magnets alter in periodic configurations, creating a local polarization of the field, but no total magnetization. So these magnets might appear to be antiferromagnetic, but the point is that they have these interesting stable structures in the polarization. What they did in the new papers is that they confirmed for the first time that some types of crystals actually have this magnetism. It's been there all along, basically. It's just that no one knew it existed. Why is this interesting? Well, first of all, it's fascinating that they discovered a completely new class of materials, and it's not even stuff that needs to be synthesized in a complicated way. One of the compounds they used is ruthenium oxide, which is maybe not exactly on your friend list, but popular enough to have a Wikipedia page and be available for order online. But besides the general interest, these magnets might be useful because their alternating patterns can be used to encode and transport information, and that could be handy for electronics, maybe even for quantum computing. And just in case you thought you understood it, there's a thing called ferrimagnetism. Phasing out nuclear power is the dumbest thing the Germans have ever done. Each time I say this on Twitter, people come and tell me that Hitler did a few things that were even dumber. I disagree. Hitler wasn't dumb, he was evil. He knew full well what he was doing. I'm not at all sure the current German government knows what it's doing, and that isn't a good thing either. The German opposition to nuclear power is especially curious as our next-door neighbors, the French and Dutch, have no hesitation to use nuclear power to its full potential. Indeed, companies in both countries recently teamed up to bring small thorium reactors to Europe. Let's have a look at what's new. The news is that two companies, Narea of France and Thorium of the Netherlands, have signed a partnership agreement to work on thorium-fueled small nuclear reactors. Thorium, as the name indicates, specializes in using thorium as nuclear fuel. Narea is already working on small nuclear reactors, and they want to combine their technology with the thorium cores from the Dutch. In case you're wondering what their logo is supposed to show, that's a radish. Yes, a radish. Because as they explain on the website, the radish is a root vegetable that leaves no waste as the entire plant is edible. I looked it up and you know what? It turns out that radish leaves are indeed edible. I had no idea. Okay, but back to nuclear power. Small modular reactors have in recent years received a lot of attention. The idea is that rather than building one huge and expensive nuclear plant at location, you build smaller reactors that can then be transported to the place you want them. That they're modular means you can combine them to get a higher power output. Saying that they're small is maybe somewhat of an overstatement, not like you can put them into your pocket, but they're just about small enough to be put on a truck and be transported on the road. Small modular reactors have the potential to solve the two biggest problems of nuclear power at the moment, which is that building nuclear power plants is expensive and it takes a long time. Though if the small modular reactors will actually solve those problems, only time will tell. The two companies who have signed the new agreement say that they want to cater in particular to the industry, where such a reactor wouldn't be connected to the public electric grid. This makes a lot of sense, because that way they can be put to use even faster. Suppose you have some energy-intensive process in the manufacturing industry. Just take the factory off the grid, plug it into a modular reactor, and the carbon footprint goes down dramatically, regardless of what the rest of the country does. You can also use the heat from the reactor directly rather than making electricity from it first, which improves efficiency. The two companies each produce somewhat different reactors though. Narea is working on what they call an extra small nuclear reactor that'll generate roughly 40 megawatts of electricity, and they hope it'll be done by 2030. Horizon is working on a reactor with roughly 100 megawatts that is targeted at larger industrial customers. They want to have a pilot system ready before 2035. But let's talk a little more about those thorium reactors. Almost all currently operating nuclear reactors run on uranium. The only exception is one reactor in China which runs on thorium, though there are a few small test reactors in the works, and there are also some reactors like the Candu reactors that can run on either thorium or uranium, though they all currently do run on uranium. Thorium has attracted attention in the past decades as an alternative nuclear fuel because on Earth's crust it's about 3 to 4 times more abundant than uranium. It also can't be as readily used for nuclear weapons, though if you make some effort, that's still possible. The real advantage of thorium reactors is, however, that they can use essentially the entire thorium, not just a small fraction of it as it's the case with the normal uranium reactors. This, I assume, is why Narea has the reddish as a symbol, though maybe it means that their reactors will be red with green leaves on top, you never know. That the thorium can be used almost entirely means that the thorium reactors produce more energy from the same amount of fuel as uranium. As a consequence, thorium could last for thousands of years. Thorium is also a waste product of the rare earth mining industry, so trying to put it to good use is a good idea. The downside is that since there's currently no dedicated thorium mining, it might go into short supply quickly, so there are some commercial challenges ahead. The small nuclear thorium reactors work not with solid fuel rods, but with the fuel dissolved into a liquid salt. This is why they're called molten salt reactors. Modern molten salt reactors, as all newer reactors, come with passive safety features. This means that in the case of a loss of power, oxygen mask will drop out from the panel above your head. Just checking if you're listening. In the case of a loss of power, the nuclear fuel will be automatically dumped into a place where it'll cool rather than in earlier reactors go on to heat up and potentially cause the core to melt. That said, nuclear power is still dangerous, and I fully understand that many people are opposed to the technology because of the risk. However, everything has risks, and I think one also needs to take into account the risk of not using nuclear power, because that means continuing to use other sources of energy which also have risks. Nuclear power technology has changed a lot in the past 50 years, and I really think Germany is missing the bus by not investing into it. So in case you're from the German Parliament, denkt noch mal drüber nach. Thanks for watching. See you tomorrow.